Good evening. Welcome to Krishna's classroom. We have been discussing the completeness of metric spaces. And we have characterized completeness. And we have also looked at some examples of complete metric spaces which are non-trivial. But now it is time for us to have a look at an important function space which is not complete. We call that CAB with soup norm, that is denoted by norm infinity, is a complete norm linear space. And therefore it's also a metric space which is complete. Now what we do is we change the norm. Later on when we do functional analysis, we will realize that the same space can be fitted with various norms which are not necessarily equivalent. Especially when we work on infinite dimensional spaces like function spaces. Now we look at this one, CAB, the same set of objects with what is called a norm 1, L1 norm, where norm of f is defined as integral a to b mod f and this is of course see that this norm is well defined and you can show that this is a norm, and consequently we have the distance function d1 fg defined as integral a to b. If you want, you can write d mod this is the metric d1 metric that is induced by the norm. Now this, what is the status of this space? Is this also complete? Is CAB now we shall prove that this is not complete, although this is a complete non-linear space. So we have CAB with the norm infinity is complete, whereas CAB with the norm 1 is not complete. They are the same objects, but now what is happening is that the length concept is changed and consequently the distance concept is changed. Therefore they are metric spaces made up of the same objects, but with the distance notion or distance notion or the length notion totally different, and then we see that it affects the completeness. Now this is a very interesting example. Yeah. So let us state the theorem. Theorem is this is that See, for convenience or for the handiness of the notation and computations, we choose a to be equal to minus 1. We choose a equal to minus 1 and b equal to 1. So that we are working on the interval minus 1 to plus 1. Here C with is not complete normal linear space, and therefore it is not a complete metric space. Now this choice has been purely for this. Now you see, it's quite easy to rework the whole thing. For if you have an interval AB, then to go from there to minus 1 to plus 1, it can be achieved through a translation and a dilatation. These are continuous maps. So you can easily use this theorem to prove that CAB with the norm 1 is not a complete normal linear space. So we'll prove this theorem. So we have to show that there exists a sequence of functions in C minus 1 plus 1 which does not have a continuous function as the limit. In fact, we show that, or we construct a Cauchy sequence of continuous functions on the interval minus 1 plus 1, which converges to a discontinuous. So that's the method of proof for that we sorted. So let us recall, take X to be norm F so that you have D1 now clearly, I mean, one can show that, easily show that is a norm on one. And therefore, D1 is a mid, which implies D1 as defined above is a which implies T1 Let us take the following sequence. So let us geometrically look at our strategy. Our strategy is this. Now we define a function which is 0 identically on the interval -1 to 0, and from 1 by n to 1 the function is defined as equal to 1, and then in between these 2 points, that is the point 0, 0 and 1 by n 1 are connected by a straight line segment. Now what would happen as n tends to infinity? See that as n tends to infinity, 1 by n goes towards 0. Therefore what happens is you will get more and more of this function becoming 0 here and then 1 over here, and eventually what happens is as n tends to infinity, 1 by n goes to 0, and consequently from on the interval 1 by n to 1 the function is identically equal to 1. Therefore what results is a discontinuous function with discontinuity at the point 0. Okay, so that's the strategy, but we have to prove all this. These are all the intuitive observations that we make from the geometry of the situation. So let us define this function. The function is defined as fn x equal to 0 for t belonging to and equal to nt for t belonging to 0, 1 by n and equal to 1 for t belonging to that's our definition of function. Now you can easily see that it's a continuous function on the interval -1 to +1 for each n. So you have a sequence of functions Fn now, your Fn. This is the graph of. Now we first show that this is a Cauchy sequence in the D1 matrix. So Fn D1 matrix. So that's our next observation, or we prove this result. So we have to estimate this. So let us take n greater than. Then we have this is equal to, we split the integral into -1 to 0 of mod n minus fm plus integral 0 to 1 by n plus integral 1 by n to 1 by m integral 1 by m so the domain is split into 4 parts with n greater than m. Do this splitting, and now we can write this as I1 plus I2 now we estimate each one of these integrals. You can easily see that I1 is equal to 0 because both Fn and Fm are 0 there, therefore I1 equal to 0. Similarly, I4 is also equal to 0 because the function, both these functions are identically 1 on that interval, and therefore this is 0. So I1 and I4 are 0. So we will now estimate I2 and I3. I2 is essentially integral 0 to 1 by n minus m now that we can calculate this is equal to n minus m divided by 2n square. 2n square and this is bounded by n divided by n square. That's an upper estimate for that. Therefore, we get I2 is less than or equal to 1 by n. So this is the estimate that we get. Now we estimate I3. Now we estimate I3. So I3 we shall evaluate and then find a bound for that. So I3 is and that is less than or equal to Dt, and that is less than or equal to 1 by m 1 by n, which is equal to n minus m, which is less than or equal to n divided by nm, which is equal to 1 by. Therefore, I3 is less than or equal to. So what do we have? Therefore, we have, and I4 is of course equal to 0. Therefore, we have norm Fn minus Fm 1 is less than or equal to 1 by, which you can write as less than 1 by n plus 1 by. Okay. Now we shall make use of this estimate. So for positive, choose n greater than 1 by. Now such an n exists by Archimedean principle. And now let us estimate this. What is the consequence? So n is greater than 1 upon epsilon, and choose n greater than m greater than or equal to n, then norm of is less than or equal to to epsilon. Okay, this is true for every nm greater than or equal. That implies so we have proved that the given sequence or the sequence that we have chosen is a Cauchy sequence. Now we try to work out the limit of this. Okay. So we prove that continuous function on -1. Now suppose there exists an f which belongs to such that goes to 0 as then we show that this leads to a contradiction. Or effectively saying that this is not possible. There does not exist a continuous function on the interval -1 to +1 which is the limit of the sequence Fn we have constructed. Let us do the necessary estimation to prove this part. Now you see, if f is continuous on -1 to +1, then f is continuous their restrictions to these two parts are continuous functions. So we shall use that. Okay. Now once again, let us estimate that. So we call this the integral J1. So each of these terms is a non-negative. J1, J2, J3. Each of those should as that is the observation that we shall use this. Now you observe that Fn is equal to 0 on minus 1 to 0. Therefore, we have the first integral J1 equal to integral 0 to 1 see that J1 equal to 0 and this is essentially integral minus 1 to 0 mod f dt. The reason is this, that is, since Fn is so you see that for all n and J1 goes to 0 as n tends to implies and you see that mod f is a continuous function continuous on 0 and hence so we have proved that f is identically equal to 0 on the interval 0 minus 1 to 0. Now let us estimate the other terms. Now let us take J3. Infinity. Okay. Now fix n. Which is equivalent to saying that 1 by n 1 by we have Fn identically equal to 1 on 1 by n to 1. Therefore, J3 is hence Fn, which is equal to 1 by n to 1 mod f minus 1. And you see that f is assumed to be continuous on the interval 0 to, now f belongs to C one, and 1 is of course continuous, which then implies that f minus 1 is continuous, so mod f minus 1 is continuous, and on this interval this is equal to 0. Integral 1 by n to 1 equal to 0. This goes to 0, which implies integral 1 by n to 1, which implies, since this is a continuous function, we have on 1 by n to 1, or at least on this part, it's a material at one point. Now this is true and f is equal to 1 on by n to 1. What is the implication? Of course, J2 goes to 0. Thus, we have this is true for every n. We have identity equal to 0 or -1 to 0 and f identically equal to 1 or 0 to thus the limiting function f has a discontinuity at t equal to 0. This is inevitable. Okay, which shows this is a conversion. Therefore, the sequence essentially converges to a function which is not. Okay. Thus, discontinuous function on implies Fn does not converge to a continuous. Does not converge to a continuous. That is C minus 1 1 is not complete. So this is an example of a normally linear space which is not complete, and consequently an example for an incomplete metric space. So let us look at some other examples. Consider the sequence space C naught consisting of all sequences real numbers converging to 0. Define x. So x you take as xn. Xn goes to 0 as n tends to infinity. And norm of x you define as the supremum of over x. Then C naught is a normed linear space, and one can prove that, and hence metric space. Now one can prove that another example of an incomplete sequence space is the following. Now consider, it's the first example. Second example is take C naught dot. This is the set of all sequence xn and this n would depend on, that is, now this means all but finitely many xn's are 0. That's an limit. So this n may depend on the particular function. It's not that all sequences end at xn. That's not the case. So I'll just give a now this sequence, now this space. It's a vector space, obviously, with the norm now you see that this is a norm. It's a normed linear space. So C naught naught outcome. It's quite easy to prove this. Consider the sequence. equal to 0 or k greater than or equal. So the sequences, the elements are 1, 0, 1, 1 by 2, 0, and so on. These are the elements. This is your x1, this is x2, and so on. So xn is going to be etc. Now note that xn is a Cauchy sequence. Now note that xn is a Cauchy sequence. Oh, yeah. That's quite easy to see. You estimate the norm of xn minus xn. It's quite easy to see. It's a Cauchy sequence in C naught naught. Infinity. Now one can show that xn converges to sequence 1 by n. To infinity, and you see that this does not belong to okay. Therefore, C naught naught okay. Thank you very much. I think we conclude here, and in the next lecture we begin with the problem of construction of the completion of incomplete spaces. In fact, we proved that in some sense there is a unique completion of each metric space. So given a metric space, there exists a unique completion of that space. That's the big theorem that we are. Which, if you recall my example earlier, that trying to play football on the deck of a ship with no boundary, what we are going to say is we can actually set up a boundary and have a complete space, so that all Cauchy sequences in that space will touch somewhere. That means we have to adjoin more elements into this class to make it. A example is C naught naught. Now you see, you have to, you know that it's a part of C naught, and therefore you have to bring in elements from C naught to make it complete. So its completion is actually C. Thank you very much.